Okay, today we're going to talk about reactions of 1,3-dicarbonyls and also elaborate on the Claisen condensation a little bit further. Now, the Claisen condensation the products are 1,3-dicarbonyls. But they also have another requirement. They need to have a hydrogen on carbon 2. So this is carbon 1, 2, and 3, giving you the 1,3-dicarbonyls. A hydrogen on 2 is essential to be a Claisen condensation product. This can be made from a Claisen. This can be made from a Claisen. This, on the other hand, cannot be made by a Claisen. At least, not directly. And that's because the Claisen condensation is thermodynamically unfavorable. What do I mean by that? Well, say you have a Claisen self-condensation, meaning between two identical esters. The Claisen product such a reaction would be this. So you start out with two esters and you end with a molecule with one ketone plus one ester. Well, so you do a mixed Claisen reaction using a ketone and an ester. So you start off with a ketone and an ester, and the mixed Claisen product would be a diketone. In each case, an ester is exchanged for a ketone. Esters are thermodynamically more stable than ketones. So as a result, each of these reactions, they're reversible reactions, but they are uphill reactions, making the favored side the starting material side. So let's do the mechanism of, say, this self-condensation reaction between this molecule right here and sodium methoxide and methanol. Well, if we were to do this reaction, start off first by deprotonating. Forming the enolate. And then this enolate reacts with the carbonyl. And then the electrons swing down and kick that off. Giving you this product. If we were to show the reaction energy of this, you start out with the deprotonation to give the enolate. And then attack the enolate to give the tetrahedral intermediate. And then this goes down and kicks that off. To give this product right here. And all these steps are reversible. And when you have a reversible reaction like that, the lowest energy side is favorable, and the lowest energy side is right here. Now, I'm going to cheat just a bit. What I'm going to do is I'm going to copy this. And drag it down. Well, I'm going to try to copy it and drag it down. There we go. And let's talk about what would happen if instead there was a hydrogen there. Hydrogen there. So if we were to do that, we would get rid of that carbon, that carbon, that carbon. Oops, not both of them. That carbon, that carbon. Okay. So that's cheating just a little bit. But when this O- is kicked off, unlike before, now there's a hydrogen in place. And this hydrogen is acidic, and so the base can take that hydrogen off. And this is the fastest step in the reaction. And what we end up getting is a significantly weaker base than the methoxide. And this is a very fast reaction, so the activation barrier of this is small. So let's move spin this guy over just a bit. We have a very small activation barrier. And it goes down to here. Now what we have is the lowest point in the reaction is over here. And because of this step right here, this last step, it drives the entire reaction forward to this product. So the product that you get is not really this product, it's actually the enolate. The deprotonated version of this product. And that's lower in energy, and that reaction drives it. This is what's sometimes referred to as a thermodynamic trap. Because if you didn't have this trap, then the lowest energy state is on the left side, the starting material side, and the reaction would progress backwards. In order for the Claisen condensation to work, it must deprotonate the center carbon. It must go too far. It has to fall into this thermodynamic trap. So the product of this, the Claisen condensation, is technically the enolate. And by the enolate, you can draw either one of these. They're just resonance structures of them. And you need the H3O plus to put the proton back. Give that. Okay. As a result, if you had molecules like this, they have a tendency to undergo the reverse Claisen. Sorry, not reverse Claisen. Reverse Claisen, or sometimes it's called the retro Claisen. It's a common side reaction of these. where you can have the base acting as a nucleophile attacks a carbonyl. Followed by protonation. And that gives you these molecules. This molecule right here comes from the base instead of attacking the right-hand carbonyl. This molecule comes when you attack the left-hand carbonyl. And so as you get a complex mixture. Now, you are fully capable of making these compounds, but the key is not using a Claisen condensation directly to make them. So one synthetic method is called the Malonic ester synthesis. Well, you take a molecule that has a dicarbonyl, in this case a diester. This is called dimethyl malonate. The center carbon has a pKa roughly around 10. And what you're able to do with a base is simply just deprotonate it and form an enolate. Now this enolate has a conjugate pKa of 10. It's a moderate base, fully capable of doing SN2 reactions with even secondary carbons. Now this step right here, all it is an SN2. You cannot do this with tertiary carbons or tertiary bromides because of the E2 reaction would outcompete and you get an alkene. But here it's just simply an SN2 reaction. Like that. Now, it's possible to deprotonate the center one, again, only when you're trying to deprotonate the center one, you want to use a more hindered base and solvent, like terbutoxide and terbutanol. We'll get to why after a bit. And then you can go ahead and do another SN2 reaction with another secondary bromide or primary bromide or methyl bromide. Just can't be tertiary. Like so. Okay, Now here's the neat thing about this reaction. You can stop here if you like, but you can also hydrolyze the two to give this compound. You could have also used saponification followed by H3O plus, and that would give you the same results. All you're doing, this is the acid and water is just the reverse of the Fischer esterification or saponification. That you're changing an ester into a carboxylic acid, and these compounds are called beta ketoacids. And a beta keto acid is special because when you heat up a beta keto acid, you end up losing carbon dioxide. It's what's called decarboxylation. And it is unique to beta keto acids. Okay. What a beta keto acid is you have a carboxylic acid. Here's the alpha carbon, here's the beta carbon. You have a carbonyl on the beta carbon. And that is key. Because what you can do with this motif is you can draw the structure like this. And when you have a structure like this, it decarboxylates upon heating. The mechanism of that is the following. What you do is you form this cyclic transition state where the electrons from the double bond O grab the H, the electrons from the OH bond swing to here, create the oxygen-carbon double bond, and that kicks these electrons over. What you end up getting is this compound and carbon dioxide. This compound is an enol. And enols tautomerize. Into carbonyls. This particular one ends up going to a carboxylic acid. This is not a beta keto acid. So it does not lose a carb. It doesn't undergo decarboxylation. The net result of the malonic ester synthesis is you're able to create very complex carboxylic acids with different R groups next to it. Now, let's talk about this reaction right here. Why you need that. It's used to minimize the retroclaisen. So the way this reaction works is you have a flask, and it's filled with your alcohol solvent. And your dicarbonyl. You add in your alkoxide to that, and you get the deprotonation. But you also have a bit of lingering RO minus in there. Then you add in your SN2 electrophile. And this is present in, does the SN2 reaction, and you end up with a little bit of RO minus and alcohol left with your product. Now this product right here can undergo the retroclaisen. That can end in giving you byproducts. Remember, the retroclaisen is the RO minus tax. So let's go up. Form a tetrahedral intermediate. Electron swing back down. If it kicks off the OR minus, you're right back where you started from. If it kicks off the other group, you've done a transesterification. Or if you kick off the carbonyl containing group, you do the reverse retroclaisen. You do the retroclaisen. Added too many double negatives there, so you just end up doing the retroclaisen, getting this as a byproduct. Okay. When your RO minus is terbutoxide, this is minimized. The reason why has to do with your first step, adding to the carbonyl. You're going from an sp2 carbon with 120 degrees to an sp3 carbon, the tetrahedral intermediate, 109.5 degrees. This is sterically crowded. And when that R group is equal to a tert butyl group or other bulk group, it becomes too crowded to really form. It really reduces the instances of this actually going on. And so as a result, you're blocking this attack, and that stops the retroclaisen. At least it minimizes its effects anyways. Now you can do this type of dicarbonyl type synthesis with other molecules. For example, you could do it with this molecule right here. It's called an acetoacetate. This one is acetylacetones. It can be used to put two R groups on the center carbon. This problem is going to be in the problem set. Okay. And this goes via this intermediate, which is essentially another beta ketoacid. Okay. Now, I've got one other reaction to show. And what you can do is use LDA to deprotonate 1,3-dicarbonyls. And what LDA does is it deprotonates the most acidic hydrogen first, and if there's a tie, it goes to the less substituted one. Or I should say the less hindered one. What we have here are 3 protons. This has a pK roughly around 20. This has a pK being between the two is 10. This has a pK being on the end 20. So what LDA does is it selectively pulls off the middle proton. And I'm going to draw this in the minor resonance form. For illustration purposes. Turns out LDA is quite capable of deprotonating this again. These two hydrogens, their pKa's are likely to be higher than 20 now because of the presence of the carbanion, but the LDA is still capable of pulling them all both off. They have near equal acidity, so it goes to the less hindered one. Like so. Now this is the minor, very minor resonance structure. The major resonance structure of this compound would be like this. Okay. Now the neat thing about this type of intermediate is you have two lone pairs. And what you can do is take advantage of this. If you had one equivalent of an alkyl halide, and here the R group should be methyl or primary carbons. This is very basic. Secondary carbons and tertiary carbons have a tendency to give E2 reactions. You can get near selective alkylation at the end. And that's because the red lone pair is delocalized amongst two carbonyls. The blue lone pair is delocalized amongst just the one carbonyl. It's more localized at that carbon, therefore it's more reactive. And then that gives you this. Now, with this molecule right here, you can pronate it. And what you're able to do is add an R group, not by deprotonating the most acidic proton, but by deprotonating the second most. Or what you could even do is add a different alkyl group. I'm out of space. Let's just redraw that down here. Now, this carbanion is considerably less basic than the previous dicarbanion. Since it's less basic, means it's less likely to give E2 products. So R prime can be methyl, primary carbons, or secondary carbons. And you can get alkylation there. And so we have essentially created carbon-carbon bonds, and we can do it selectively on either carbon that we want. Okay. That's what I have for today's lecture. On Friday, we will talk about the Michael reaction. In fact, let's go ahead and give you sort of a preview of the Michael. So here's a preview of the Michael reaction. And by preview, I'm going to show you the breakdown of the Michael. Michael products are 1,5-dicarbonyls. like this. And the way you break down a Michael is you break the 2,3 bond. This is just like the Claisen breakdown and just like the aldol breakdown. Carbon 2 gets a hydrogen. That's just like the Claisen breakdown, just like the Michael breakdown. Third one, what makes them different, is carbon 3, carbon 4. They get a pi bond. So here's 1, 2, 3, 4, 5. 3 and 4 get a pi bond. Now, since there are two carbonyls, it's possible to number them either way, just like the Claisen condensation. However, unlike the Claisen condensation, it may or may not work. The important thing is a Michael product is a 1,5-dicarbonyl. Carbon 4 must have a hydrogen. If carbon 4 doesn't have a hydrogen, then you don't want to break it down that way. What I mean by that, try renumbering it backwards. So this is carbon 1. And then try doing the breakdown on this pattern. And hopefully you see why carbon 4 must have a hydrogen. Okay, let's do that. One, 2, 3, 4, 5. Do the Michael. Break the 2,3 bond. Carbon 2 gets a hydrogen. Three, 4 gets a pi bond. And there's the issue. You end up with 5 bonded carbon. So you have to be careful on that. Okay, we'll go over the mechanism of this as well as the uses of this reaction on Friday.